Welcome to Unit 7. This is the conclusion of the class. I hope everyone's enjoyed it and learned a lot about cryptography. I'll summarize the class briefly, and then I will talk about one new protocol and one new application of cryptography to do secure computation. One important point that I want to make today, that I haven't made throughout the class enough, is that cryptography is very different from security. When we're thinking about cryptography, these are very abstract things. We're thinking about whether we can use math to solve problems. On the other hand, security depends on a lot more than just cryptography. Security is really mostly about people. No matter how good your math is, if someone picks 1, 2, 3, 4, 5, 6 for their password, it doesn't matter. You're not going to have security. Security is also about systems and how they interface with each other. Many of the security problems are because of misunderstanding the connections between systems. In this class, we've largely focused on cryptography and not addressed the broader issues about security. But if you want to build secure systems, well, these issues are very important. It's not just about the math. Cryptography is all about secrets, and we've seen lots and lots of ways to use secrets to solve problems. We started in Unit 1, looking at the one-time pad, where we could XOR a message with a key. And we saw that that provides perfect secrecy in a strong theoretical sense, that an eavesdropper who intercepts this message can learn nothing at all about the message, but that it requires a perfectly random key that's never reused, that's as long as the message. So it doesn't work well in practice. It also has all sorts of other problems, like the malleability of the one-time pad. This led us in Unit 2 to look at some ways to use practical symmetric ciphers to provide nothing close to perfect secrecy, but something useful for many purposes. We saw that we could amplify the security provided by a small shared key to obtain a secure channel for sending long messages, and we talked about modes of operation that can do that with different levels of security. And then we talked about cryptographic hash functions, which provide a way to map a message to a smaller value that provides pre-image resistance, so it's hard to find a message that hashes that value, as well as collision resistance. And this is useful for authentication, as well as lots of other purposes that we've seen. The big limitation of symmetric ciphers is they require a shared secret between the two parties. In Unit 3, we talked about key distribution, focusing on the Diffie-Hellman protocol for key agreement, and that allows two parties to establish a shared secret starting from an insecure channel. That led to asymmetric crypto systems, in particular RSA, as an example of a public key crypto system, that provide the additional functionality where the encryption function doesn't reveal the decryption function. This enables lots of interesting uses of cryptography. In Unit 5, we saw how to use public key combined with symmetric ciphers to provide authentication. And we focused in particular on the TLS protocol that's used as the basis for electronic commerce on the web. In Unit 6, we looked at protocols for anonymous routing, voting, and digital cash, all of which combined a mix of asymmetric and symmetric crypto systems. So I hope you've enjoyed this tour of cryptography. We've seen lots of different things that can be built from a few simple primitives. I'm going to cover one more protocol this unit, which is looking at secure computation, and it uses many of the tools that we've seen in all of these previous units. So here's the goal of secure computation. Let's suppose Alice and Bob meet at a conference. They don't yet know each other, despite the fact that they've been talking with each other through units 1 through 6, but let's pretend they're not quite so friendly yet. And they both have their smartphones. And on their smartphone, they have an address book. And what they want to do is figure out, do they know any of the same people? This is a pretty common occurrence at conferences. Often the way people do this is the slow, were you ever at this place? Do you know someone here? Do you know anyone there? They want to do it more efficiently. So what they'd like to do is have a protocol that allows them to compare their address books, find all the people they know in common. So in this case, it would match Dennis, since they both know the same Dennis. And then they would see the matches, but not reveal anything else about their address book to the other person. They want to do this by executing some protocol, where at the end of the protocol, both parties would know the matching entries, but not learn anything else about the other person's address book. More generally, we have two parties, A and B. They have some private information. They want to perform some secure computation. And at the end of that, they learn the result of some function on both of their inputs, but they don't learn anything about the other party's input. So now it's time for a question, sort of a trick question, but if you were paying attention at the beginning of this unit, you'll be able to answer it correctly. Can we achieve this property using cryptography? The answer is no. We're going to talk about a cryptographic protocol that does this, but actually achieving what we want depends on lots of other things. It depends on people. It depends on assumptions about the adversary, knowing what capabilities the participants have, as well as any eavesdropper might have, as well as building the system that actually runs the protocol. So these are all things we're not going to talk about. What we are going to talk about is a protocol that, given the right answers to these questions, could provide this property. This idea was developed by Andrew Yao in the 1980s, and it gives a way to perform any function as a secure computation. And the idea is that any discrete fixed-size function can be turned into logic gates, and then if we can find a way to implement logic gates securely, we can implement a whole function this way. So we can think of a logic gate as a truth table. Let's take, for example, the function and. And takes two inputs and produces one output. And we can describe that and with a table of values. We'll use 0 to represent false and 1 to represent true. So this is a regular AND gate. And if we evaluate the AND gate, well, we need to know the actual values of A and B. Suppose the value of A is 1 and the value of B is 0. Then we would take this line from the truth table and know that the output has the value 0. And our goal is to encrypt this circuit in such a way that we can still evaluate it without actually knowing what the inputs are and without learning what the output is, but still produce an output that we can use as the input to the next circuit. If we can evaluate each gate this way, keeping the inputs and outputs encrypted, we can evaluate the whole circuit, and at the end, we can map the final result to a meaningful value. So our first step to creating an encrypted circuit is to replace the inputs with encrypted values. That means we need some way to represent a 0 on this wire and some way to represent a 1. Same for this wire. So we're going to replace these 0s and 1s in the table with encrypted values. We'll just look at those as random nonces. So we're going to pick some random value to represent 0 on this wire. Let's call that A0. We'll pick some random value to represent 1. We'll call that A1. And we'll do the same thing for the other wire. And we'll do the same thing for the output. So here's our new truth table. Well, if we keep things in the same order, we haven't hidden anything. So let's randomly permute it. And now suppose we get a table like this. That means that A0 is either 0010 or 1010. So now the question is, can you determine what is the value of B0? If you could, well, that would mean you know the semantic value of B. So you can tell if it's equal to B0 or not. And that would mean you're evaluating the circuit and you're learning the values in the circuit, so you don't have the secure computation you wanted to. Can you determine the value of B0 knowing this garbled table? And the answer is you can, that it must be 1100. The way to see that is if you look at the x values, well, there are 3 that match 0, 1, 1, 1. Those must correspond to the output where x equals 0, because we know an AND gate has 3 outputs that have the value 0. And then there's 1 that has the value 1011. So that must correspond to the x value having the output 1. And that means the only way the output could be 1 is if both of these represent 1. So that means we know the value of B1. That's this one. So the value of B0 must be the other one, which is 1100. And we can, in fact, deduce all the lines in the truth table from this pattern. So obviously this doesn't work. We're not hiding the patterns that are inherent in the logic functions we're computing by replacing them with random nonces. We have to do something so this table is harder to see. And what we have to do is make it so the outputs are encrypted, that we can't tell the values of the other entries in the truth table. We can only tell the value of the one that we actually evaluate, and that hides whether it matches any of the other values. So we need to hide that pattern, and the way to do that is going to require encrypting the outputs in some way. We have to encrypt them with different keys, though. If we encrypted them all with the same key, well, then either the evaluator would be able to determine all the outputs, because the evaluator knows that key, or she couldn't determine any of them because she doesn't know that key. So we need to encrypt each output with different keys, such that when someone evaluates the truth table, they can only decrypt the output that corresponds to the row for the actual values they have. So the question is, which of these values could be used for this entry in the truth table to ensure that a circuit evaluator who knows A1 and B0 will be able to decrypt this output and none of the other outputs? Here are the choices. Be careful that more than one of these could be correct. So the answer is the last 2 could work. Let's go through the other answers. So the first one, we're encrypting using A1, the value of x0, concatenating that with encrypting x0 using B0. This means if the evaluator is either A1 or B0, they would be able to learn the value of X0. That would enable the evaluator to decrypt more than one entry in this truth table if the other entries were encrypted the same way. The second possibility has a similar problem. If the evaluator knows A1, they can obtain the value of X0. That's not secure because they can decrypt two outputs in this table. The other two make it so that obtaining X0 depends on both keys. It depends on knowing both A1 and B0. An evaluator who knows only one of those can't determine the key for this encryption, since this is the XOR of those two values and it depends on both of them. They also couldn't do both of these. They could do the first one if they know A1, but they just get an encrypted value there, and they couldn't decrypt the second one to get the value of X0. So either of these could work. This first one's going to be more efficient because it only involves one encryption. There might be other ways to combine the keys that would be better and provide more security. That means in our garble table, we'll have our outputs encrypted with different keys corresponding to inputs that correspond to that output value. Of course, we can't just send that whole table. That would reveal the values of A0 and B0. So we need to remove this part of the table. And then we need to randomly permute the order of these entries. The other thing we'll do is add some padding. So that means after the garbling, we'll have a table that looks like this. Because each of these values is encrypted with a different key, the evaluator can't tell which one is which. The evaluator still needs to be able to decrypt these to produce the right output. So the question is, how does the evaluator know what the output of that truth table is? The evaluator could try decrypting all the entries and pick the one that seems correct. The evaluator could try decrypting all the entries using the input value keys known to the evaluator and use the one that decrypts to something of the form pad concatenated with X and then use this value as the output. Or it's not possible based on what the evaluator knows. The answer is the second choice. The evaluator needs to try decrypting each of these. It knows one of the A values and one of the B values, but it doesn't know which one it knows. The ones that aren't correct, well, it's going to have the wrong key. It's going to decrypt some message, and it won't start with this pad. That needs to have enough bits, so the chances it would start with this pad if it's not the right key would be vanishingly small. And the one where it does have the right keys will decrypt to the pad and the correct output value. And that's the value, that's the output for that gate. So here's how this works as a protocol. We have two participants. We'll call Alice the generator. That means she's going to make the circuit. And Bob the evaluator. That means he's going to evaluate the circuit. At the beginning of the protocol, they've agreed on some circuit they want to evaluate. For this to be interesting, it would be much larger than that. And it takes inputs from both Bob and from Alice. Alice is going to generate a garble table for each one of these logic gates in the circuit and send the garbled circuit to Bob. She's also going to send her input values, but because they're random nonces, Bob can't tell what they mean. Bob's going to evaluate the circuit using the garbled circuit protocol, decrypting one entry from each of these. And at the end of this, Bob's going to get some output values. And then they're going to do something to turn that into the semantic value, which possibly Bob receives, possibly Alice receives. We can design the protocol either way. And I'm not going to talk about that final step of how you turn the encrypted values at the end of the circuit into meaningful values. We'll leave that as a question for your exam. But there is one more question that I do need to talk about. That's the question of how does Bob obtain his inputs to the circuit? To evaluate these tables, Bob needs to know both Alice's inputs and his inputs. So here are the choices. Well, Bob could generate them himself. He could ask Alice to provide his inputs. He could ask Alice for both possible values for all of these wire labels and then select the right one corresponding to his inputs. Or none of these possibilities actually work. The answer is none of these work. He couldn't generate them himself because if he generated them himself, there's no way Alice could generate these garble tables. He can't ask Alice to provide them. That would require him to reveal his input, and the whole point of this protocol is for him not to have to do that. This approach wouldn't work either. If Alice gives Bob both of the values for each input, well, then he can evaluate these gates with both of those values, and he can learn more about Alice's inputs than he should. So the answer is none of these work. We need some other solution. We need some way to enable Bob to obtain these inputs without revealing to Alice what Bob's actual values are. What we need is something called oblivious transfer. And in particular, we need what we'll call 1 out of 2 oblivious transfer. And what that means is Alice can create two values, x0 and x1. Bob will obtain one of those values, but Alice doesn't learn which one Bob learned. Bob can only obtain one of the two values, but Alice doesn't know which one Bob obtained. There are lots of different protocols that provide this. The one I'm going to describe was invented by Even, Goldrich, and Limpel in 1985. It builds on RSA encryption, and we're going to look at it as we need to use it in the garbled circuit protocol. So our goal is that Alice has two wire labels. These correspond to the inputs to some gate, and she wants to transfer one of them to Bob without revealing the other one. We're going to use Alice's public key. We'll assume that's known to Bob before the protocol starts. So our goal is to transfer one of these two wire labels to Bob. The first step is to create two random values. These are separate from the wire labels. These are going to be transferred to Bob. These have no meaning. They're just two random nonces created by Alice. Depending on which wire label Bob wants, Bob has some input, either 0 or 1. He's going to pick either the first or the second of these. So he's going to pick xb is equal to either x0 or x1, depending on his value of b. Then Bob will pick some random value r. Bob's going to use this to blind the response. So he can't allow Alice to learn whether he picked x0 or x1. That would reveal his input. So what he's going to do instead is use this random value to blind the response. And so he'll compute this new value, which is the value of x that he selected, plus the random value raised to the public exponent, mod n. So we're going to hide the value of xb by adding a random value raised to the e power to it. That value is what's sent back to Alice. And Alice is going to perform two different RSA decryptions. So she knows the values that she selected for x0 and x1. She's going to subtract each of those from v. She'll decrypt it using her private key. And we'll call the first one k0. That was the one constructed using x0. And the second one k1. That was the one constructed using x1. So the question is, if b selected 1 as its input, so that means b has the value for xb is equal to x1, what are the values of k0 and k1? Select the best answer for each choice. It could be meaningless. It could match x0, x1, or r. So the answer is the value of k0 is meaningless as long as we have a good random distribution here when we raise a to the e power. And the reason for that is this value now, v, would be x1 plus r to the mod n. That's because xb is x1. So the value for k0 is that minus x0 raised to the d power mod n. There's nothing that gets rid of this random value. And there's no reason this would be a meaningful value. The value of k1, though, is meaningful, and it's in fact the value of r. And the reason for that, now the value of k1 is equal to the value of v minus x1. So that removes the x1 from that value. So that means the value of k is r to the mod n raised to the d power mod n. And this is exactly the RSA decryption that will give us the value of the message, which in this case is equal to r. So that means Alice has now learned the random r selected by Bob, and its value is stored in one of these keys. She doesn't know which one. The value of k0 is meaningless. It's a meaningless value that can't be determined by Bob because Bob doesn't know the value of d. So that's the important thing that we've done here. Is now Alice has these two keys. Depending on what value Bob picked, one of them is meaningful, has the value r. The other one is not. So now Alice is going to send a message to Bob that will allow Bob to learn the wire label. And the way she's going to do that is actually quite simple. She's just going to add these two keys to the wire labels. So she'll send these two values to Bob. So now the question is, how does Bob compute W1? And we assume Bob's input value was 1, so we picked x1 here and followed the protocol as specified. Does Bob now have enough information to figure out W1? These are the choices. Is it possible for Bob to now learn the value corresponding to Bob's input wire? And the answer is Bob can compute this because Bob knows r. Bob selected r. Bob has received these two, and the value of k1 is equal to r because that was the one that Bob sent back here. And so that means Bob can compute this. Subtracting r from w1 prime will give Bob the correct value of the wire label. Bob cannot compute w0 though, because the value used for k0 is meaningless and unknown to Bob. So this provides the property that we were looking for, that Bob can select one of the two values that are the wire labels Alice generated. Alice doesn't learn which one he selected, and Bob doesn't learn anything about the other one. So now we have the last thing that we needed to complete the garbled circuit protocol. The way Bob obtains his inputs is using oblivious transfer. And that could be done at this stage. To enable Bob to learn his inputs to the circuit, Alice sends the garbled circuit along with her inputs. Bob can evaluate the circuit. And then from the encrypted output wires, Bob can obtain the result of the circuit execution. And he could share that with Alice, or they could flip roles and do it again, and then Alice would obtain the output. We have one little step in this protocol that we haven't described yet, which is how you actually obtain that output value. The outputs for the garbled tables are all encrypted. So at the end of the execution, what Bob has is a list of encrypted wire labels. He wants to turn that into semantic output. That's left as a question for the exam. I should note that actually executing protocols like this, doing all these encryptions is really expensive. This works for any function, but it's very expensive. It's a very active research area how to do this faster. This is one of the things my research group works on, as well as lots of other researchers, to try to find ways to provide properties like the one described here, but without as much computation effort as executing the protocol that I've just described. Congratulations, you've made it to the end of the Applied Cryptography course. The world is now safe for Alice and Bob to share their secrets, or not share them, as the case may be. And I hope you've enjoyed learning about cryptography, and will join us again for a future class.